Hello.
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 I'm Zach, and I was in charge of the grabbing.
I'm Josh, and I was in charge of path movement.
I'm Jordan, and I was in charge of sensing.
I'm Joe, and I was in charge of searching movement.
And this is Team 1 from ECE 4534. The project consists of 2 rovers, a thief, and a cop. Along with that, 2 targets with metal washers on the top for magnets to hold up. And then a jewelry museum, which will be consisting of our map that the rovers will be going through during the whole project. Now, the project's goal is simple. Rover 1 goes into the field and scans the whole map such that it maps out every single obstacle and target for the second rover to see. Once the second rover receives this map, the second rover will be responsible for going into the map and then locating every single target without touching any obstacle. Once rover 2 approaches a target, it will be responsible for grabbing the target and moving it outside of the map. Once every single target has exited the actual arena, the game is over. Our network diagram was designed in a format such that debugging would be very easy. We had to utilize the JSON structure as well, and each state had a request and a response given to it in the JSON format. We will go more into depth about each state. The colors represent the different types of rovers that used it. Red is for rover 1 and blue is for rover 2.
Because we were required to use JSON for the network protocol, we decided to use Rust for the server and 3 of the debug clients. This allowed us to easily map Rust data structures directly into JSON that could be serialized and deserialized on the devices, as well as all the debug clients on the server. We created a shared library which codified the network protocol and allowed us to document it, and it was shared among 3 of the debug clients which used Rust and the Rust-based server. The server took messages and routed them to particular rovers and modules depending on what the message was. So each message was destined to go to particular targets, rather than the message encoding that data itself.
The initialization stage is the stage where all the modules are just waiting for a network message before starting any of their processes.
To exit this state, they need to be sent an initialization message. This includes the positions of the rovers, the number of targets, and the positions of the arena vertices.
After the initialization stage, the first rover moves into its searching and avoiding stages. These 2 stages are the same as far as communication protocol is concerned. The only difference is the actual physical movement that occurs with the rover. In searching, it is straight line movement, and the avoiding stage is doing left turn movement.
During these 2 stages, the same messages are sent. One of the messages is the movement message. This includes the X, Y, and angle of the rover at any given time. It's provided by the movement module to the sensor module, so it can keep track of where it is when providing sensor data to the worldview. Next is the proximity message. This allows the sensor module to tell the movement module exactly how far away the object in front of it is, so it knows when to turn.
The next state is the border state, which occurs when the rover encounters a border that is detected using the photosensor array on the bottom. This state takes time to take those sensors and try to align straight with the line of the border.
The only message sent during this state is the assumed message. This allows the movement module to request the new assumed position from the sensor module based on the arena border positions and so forth.
So the next state is the border turn state, which occurs after we have updated our position. This state is a greater than 90-degree turn away from the border that then moves into straight line movement.
And during this state, the only message that goes across the network is the movement message, which is the same movement message from before. It allows the rover to continuously update the angle as it is turning, just as it would when it encounters an object. I'm Jordan Worley. I'm doing the sensor module on rover 1. The purpose of my module is to scan all of the targets and obstacles in the arena compile that data, and send it over to rover 2 so that when they attempt to take all the targets out of the arena, they don't encounter and run into any objects and they know where the targets are. My module had 3 IR sensors connected to it, 2 on the front and 1 on the left side. The 2 on the front allow the rover to avoid obstacles that were in front of it and turn until it had finished clearing the obstacle. To use the IR sensors, I had to get useful data out of them. These IR sensors were plugged into a 5-volt source, and they produced an analog output that corresponded to the distance that was in front of them. I measured about 20 data points, the voltages of those data points, and the distances of those data points, and plugged them into Wolfram Alpha. It gave me back a cubic equation that almost perfectly mapped the IR sensor points. The points that we get are mapped onto the grid in weights from 0 to 99. 0 indicating that there's nothing there, and 99 indicating that the robot should never go there. These weights are sent in a JSON formatted packet with 3 characters per weight, and 64 at a time, because our max packet size was 256. We sent 256 of these packets, meaning that our grid was 128 by 128. It was about half an inch per grid square.
I'm Joe Gadanik, and I had the movement module for rover 1. The purpose of my module was to traverse the arena for the sensor module that I'm carrying so that it can map the entire area, so the second rover can use that to pick up its targets. The main portion of my module is written in basically 2 states, a straight line movement and a left turn movement. To make the movement data that consisted of X and Y movement as well as orientation that I sent to Jordan for mapping, to maintain a level of accuracy with that, we had to use a PID controller, which stands for proportional integral derivative. It uses 3 different types of error to calculate and maintain a steady output. We used the PID controllers to maintain the speeds of the motors to make sure that there wasn't any random speeding up or slowing down, which would interfere with our measurements.
What you gonna do? What you gonna do when they come for you? Bad boys, what you gonna do? What you gonna do when they come for you? When you were 8 and you had bad traits, you go to school and learn the golden rule. So why are you acting like a bloody fool? If you get hot, then you must get cool. Bad boys, what you gonna do? What you gonna do when they come for you? Bad boys, what you gonna do? What you gonna do when they come for you? You chuck it on that one, you chuck it on this one, you chuck it on your mother and you chuck it on your father, you chuck it on your...
The map exchange state is the state that occurs when there's a transition of the process from rover 1 to rover 2, where rover 2 starts looking to pick up targets and move them outside the arena.
So within the state, we have a protocol called request half row and half row. Request half row is the request and the response is the half row. The actual protocol structure of the half row contains 64 different weight values of the row that we requested. For example, in row 1, we would have rows 0 and 1. We would have request row 0 and 1 for that whole row. Once again, our whole grid was 128 by 128, so we had to cut it in 2 to make it 64 and 64. Target pathfinding state, what I do is I run my breadth first search algorithm that finds the shortest path to the target. After I'm in a certain range of the target, I start going into the edge detect state. Now within this state, I have 2 protocols that are actually occurring. The first protocol is request edge detect. Now that request is sent to Zach's module, and Zach will reply back with an edge detect containing 3 values: the left, middle, right value, sensor values. Now if I am in the correct orientation, the edge detect will send me 3 magical values back that says, yes, you are in range. At that point, I can move on to the distance state, in which I will do the same thing and request a distance. purpose of the distance state is for me to approach the target slower and more accurately so that I can be in range to grab. Same concept, I will request distance and I will receive a value back, a magical value that says yes, you are in distance.
From there, we'll go into the grab state. In the grab state, Josh will send a request grabbed and I will respond with grabbed, a true or false value. In this state is when I turn on the electromagnet to ensure that we pick up the target. After I've picked up the target, I will respond that I have picked up the target and we will go to the drop pathfinding. In the drop pathfinding, Josh will then move to the nearest exit of the arena where we will then drop off the target. In this drop state, it is again just exactly like the grab state. It is request drop and drop response. In the drop response, I will send a true or false value, which tells Josh that I have dropped the target or I still have control of it. If there are multiple targets, we will go through this loop multiple times. If we are on the last target, then we will then exit the loop, the project is over, and we have acquired all.
Hi, I'm Josh Chung, and I was responsible for Rover 2 and its pathfinding. So I'll briefly go over the steps that I went through, for example, the breadth first and then states of movement that I actually went through to actually complete this module. So the main purpose of my module was to acquire targets and avoid obstacles. So in a given map that gets transferred in the map exchange state, which we talked about, what happens is I use that map to identify the closest target to me and I move to that target while avoiding obstacles. I do this by doing a breadth first search algorithm. I first looked into an algorithm called A* and I implemented my own based on the A* algorithm. The difference between mine and the A* is simply I just take the difficulty value and add it to the weight. So as mentioned before, writing my breadth first search, I'll briefly explain how it actually works. So assume this is my map and these are distributed weights and difficulties of that map. I have my starting point and my end point. I'm going to briefly go over how I go from point A to point B. So notice how the starting weight is at 40. So what happens is my algorithm goes through this whole grid and finds the weight values. First, there's a little bit that goes into it, as in I actually create these weight values depending on what's actually there. So for example, this 20 would have came from a weight value and a difficulty put together. But assume that everything has been done and I'm actually just doing my pathfinding at this point. So the algorithm that I wrote will create this map for me, and at that point I just choose the value which is the lowest value to go to. The lower value means there's less difficulty going through that path. So at this point, the 20 is less than the 30, so the difficulty value of 20 would be take precedence. So I would move up. At this point, 15 is obviously less than 80, and I would move up this way. Once again, this is how I would move. I only move in a north, south, east, west type of orientation. I do not move in any sort of diagonal orientation, so it'll always be north, south, east, west. So at this point, as you can see, going with that same logic of taking the shortest weight, I would end up going up. And I would end up at my point. In this case, then I would go to the search or grab. I would go to the grab movement and say, hey, I'm at my destination, let's grab. Briefly overview of my states of movement. So what happens first is I go through the breadth first search that I wrote, and it finds the shortest path to the target. This goes block by block. At first I implemented a method where I pretty much kept an array of a path to the target. However, what this does is it actually creates an increase of error within my PID algorithm. So what I just opted out to do was actually just go block by block and search each time for each block. So within my states of movement, once I am within a certain range of my target, I start talking to my grabber module, and Zach will talk more about what happens in that state.
Hello, I'm Zach, and I was in charge of the grabber module of Rover 2. The purpose of this module was to align the rover with the target and then pick up the target after Josh made it to the correct location where the target was. I used 3 IR sensors mounted on the front of the rover to do distance and edge detecting. These IRs were aligned vertically to ensure that we got correct edges and correct distances when moving towards the target. The first step of my process was to center the target in the electromagnet. This was done by using an edge detect algorithm using the 3 IRs on the front of the rover. Josh would sweep the rover either right or left, and I would detect for the first edge by using whatever sensor was on that side, the middle, and then the opposite side. I would then send magic values to Josh telling him to stop and then center the rover at that coordinate. The next process was to get the distance. The distance to the target was used by a slow incrementation of the motor towards the target until we reached a magic value again, which I then told Josh to stop the rover. The next step in the process was to pick up the target using an electromagnet. The electromagnet was mounted directly center in front of the rover to ensure that we were correctly aligned and correctly placed the electromagnet directly over the metal washer that was located on top of the target. Our electromagnet ensured that it would pick up the washer and thus the target until we were outside of the arena border.